So the next problem I want to do is f of x equals x to the fourth minus 4x cubed. And one of the things that I really like about this function is that it has multiplicity in it, right? This is really x cubed times the quantity x minus 4. Okay, and if you guys don't remember what multiplicity is, right, that's when in algebra 2 you guys set something equal to 0, and you're like, okay, well, this one's equal to 0 at x equals 0, and this one's equal to 0 at x equals 4. But because it's a fourth degree function, this is actually considered a triple zero because of the x cubed. Okay, or if I had like an x cubed times an x minus 4 squared, my zeros would be x equals 0 and x equals 4, but this one would have an odd multiplicity, and this one, because it's squared, would have an even multiplicity. And then at 0, I'm supposed to, if it's odd multiplicity, you're supposed to wiggle through it, and at x equals 4, you're supposed to bounce off the x-axis because it's the even exponent. And there was all these rules that you had to memorize about multiplicity. But those rules they're silly when you guys can have calculus. Calculus is so much better. Okay. All right, so in any case, when I go to take the derivative, I'm taking the derivative from this format, although when I go to plug in later, I might plug in here. Okay, so I'm going to take the derivative, and I get 4x cubed minus 12x squared. And I'm going to set this equal to 0, just like I did before. And if I do that, I could factor out a 4x squared. Excuse me, and I'll have 4x squared times x minus 3. I'm setting that equal to 0. And the outside is equal to 0 when x equals 0, and the inside of those parentheses is equal to 0 at x equals 3. Okay. I also want to consider if f prime does not exist anywhere, and that's not happening here. Okay. So I'm going to make my sign chart. It's going to be an f prime f sign chart. Okay. We want to know information about, I'm going to put those two critical points on there. My derivative is 0 at those two spots. I want information about f prime first. So I'm going to plug into f prime. And I'm going to pick numbers. I'm going to look at the factored form. I'm going to pick numbers. If I pick a number less than 0, let's say I do -2. Okay, if I do a negative number squared and multiply it by 4, it's going to be positive. -2 minus 3 is a negative, and a positive times a negative is negative. If I plug in a number between 0 and 3, I'm going to choose 1. 4 times 1 squared is positive. 1 minus 3 is negative. Okay, again, I want to stress to you guys, I'm not plugging in numbers and evaluating my derivative at those numbers. I'm testing numbers and checking the signs of those answers. Okay, positive times a negative is still negative. Okay, you guys saw how I said to you earlier that you're not guaranteed a sign change. I have a lot of students that just assume that it's going to be a sign change. You have to plug in and check it, all right? And then my last plug-in is when x is greater than 3. If x is greater than 3, if I plug into the first part, I get a positive and right, because I'm squaring, and then a number bigger than 3 minus 3 is also a positive. What is it important?
Can I have your phone so I could get a certain picture?
No, baby, I'm in the middle of teaching. Okay, this has got to be positive. Okay, now where f prime is negative, f is decreasing. Where f prime is positive, f is increasing. Okay. So let me just write that on a list. I'm increasing from 3 to infinity. I'm decreasing. You guys can do it in two ways. You could say from negative infinity to 3, or if you prefer, you can say that it's decreasing from negative infinity to 0, and again from 0 to 3. Okay, the second way is more correct than the first way, but they're both effective. Okay. And if I switch from decreasing, this means I have a horizontal tangent. So I would decrease level, decrease some more, and then switch to increasing. So this is neither a max nor a min, but at 3 I do have a local min. Okay. Okay. Then I'm going to move on to the second derivative. Okay, and my second derivative, I'm going to take off the first derivative, but in the simplest form of the first derivative. So this is the simplest form of my first derivative up here. Okay, and I'm going to take my second derivative from there. So the first derivative is 4x cubed minus 12x squared. My second derivative is going to be 12x squared minus 24x. And I'm going to also set this one equal to 0. Okay, and I could factor a 12x out of here and I'll be left with x minus 2 equals 0. And so I'm going to have zeros at 0 and at 2. Okay, sign chart. It's just my number line again, but it's going to be f double prime with f this time. And I have zeros at 0 and at 2. Okay. If I plug in something less than 0, I'm going to do a negative times a negative, which will be positive. If I plug in something on this interval between 0 and 2, let's say 1, I'll have a positive times a negative, which is negative. If I plug something on this interval, let's say 3 or 10 or 162, I'll have a positive times a positive, which is positive. Again, I don't care about the values, I care about the signs. All right, and then the important takeaway is that when f double prime is positive, f is concave up. And when f double prime is negative, f is concave down. Okay, so let me add that to my list, that I am concave up on the intervals from negative infinity to 0, and again from 2 to infinity. I'm concave down from 0 to 2. Okay, and then I have inflection points at x equals both 0 and 2. Okay, so now I'm going to take all this information and I'm going to use it to very, very, very effectively graph. So I'm just going to clear some space here. Okay, and I want to be able to graph this. I'm going to post this video online for you guys, so if you need it, you'll have it. All right, so my function, I have important things happening at 0, at 2, and at 3. Okay, so I'm going to also figure out what the y values are at those 3 important x coordinates, right? Why are they important? Because I have a local min at x equals 3, and I have inflection points at 0 and 2. Okay, so if I plug 0 into my original function, I'm going to plug in this form of it. I'm going to get 0 times 0 times negative 4, which is 0. If I plug in 2 here, right, which is the same as my original, it's not the derivative, I just factored out an x cubed, but it's easier to plug into. If I plug in 2 there, I get 8 times negative 2, which is negative 16. So I'm going to have a point here. And then if I plug in 3, I have 20, I'm going to plug it in here, 27 times a negative 1, which is a negative 27. So it's going to be way down here. Okay. Okay. So now let's just look at what's happening here. So on my initial, you guys are bombarding me with messages. On my initial interval, when I'm less than 0, I have to be concave up and decreasing. So concave up and decreasing looks like this. Okay, from 0 to 2, I am concave down and decreasing. So concave down and decreasing looks like this. Okay, and then from 2 to 3, I'm still decreasing, but I'm back to concave up. So decreasing, concave up. Okay, let me make that a different color so you guys can see the difference. All right, and then my very last section, when x is greater than 3, I am increasing and concave up again, right? So increasing, concave up. Okay, do you guys see how I get my weird multiplicity wiggle? I get my low without having to plug in a million values. I get a very nicely shaped graph with very little effort. Okay, and that's the beauty of the calculus here, which is far superior to if you just found the zeros of this function and then hoped for the best with figuring out what the rest of it looked like. Right, the zeros of this function are 0 and 4, but it doesn't tell you anything about what the graph actually looks like. It does tell me that I should have drawn that over here and labeled my intercept as a 4. But it doesn't tell you about any of the curvature of the graph, about this little weird, we called it a multiplicity bounce before this class, but now it's just it's like a change in concavity there. It's a horizontal tangent and a change in concavity there, and so that's what we've got that wiggle going. All right. All right, and for those of you guys that are still here, I'm going to do one more example, and the video will be online later. Okay, we're going to look at f of x equals 1 over x squared plus 1. And the reason I want to look at something like this is because this is a crazy rational function. Okay, and rational functions have weird things like vertical asymptotes and horizontal asymptotes. And they were also really, really difficult for you guys to graph when you were in Algebra 2 and Pre-Calc. And I know most of you guys probably felt out of your depth with the way you were being taught to graph them. Most teachers just honestly don't do the best job of teaching how to graph a rational function. So on a function like this, vertical asymptote is where the denominator is equal to 0, but x squared plus 1 can't equal 0, right? I can't do x squared and get -1, so I have none. No vertical asymptotes, which means it's a weird rational function. And then my horizontal asymptotes I get by taking the limit as x approaches plus or minus infinity of 1 over x squared plus 1. And if I let x go towards either infinity or negative infinity, I have 1 divided by infinitely larger numbers. That's going to be approaching 0. Okay, so my horizontal asymptote is y equals 0. Okay, so that means that if I'm graphing this, I have a horizontal asymptote at y equals 0, I have no idea what else is going on this graph. I could find my y-intercept. My y-intercept, if I plug in 0 for x, I get 1 for y. But then on the rest of this, I don't know what this picture is supposed to look like. Okay, so instead of doing this and trying to do the guesswork, or you guys were taught to plug in points, plug in a million points, it's not very effective. Let's take a derivative. Okay, now to take my derivative, it's the number divided by stuff rule. I'm going to really write this as x squared plus 1 to the negative first power, right? 1 over x squared plus 1 is the same thing as x squared plus 1 to the negative first power. And when I take my derivative, I'm going to drop down the exponent and reduce it by 1. The inside is going to stay the same, times the derivative of the inside. Okay, and I'm going to simplify this. I'm going to have a negative 2x on top over x squared plus 1 quantity squared on bottom. Okay, if I set this equal to 0, it's happening at when the numerator is 0, so at x equals 0. A little quick check, especially for rational functions, f prime does not exist. There's no situations where that's possible because my denominator can't be 0. All right, so I'm going to make a sign chart for f prime with just the one critical point on it. Okay. And with this, if I look at the denominator, the fact that the part is squared means that it's got to be positive. So I'm really only looking at the sign of the numerator. Okay, so those big picture ideas and pattern recognitions are good critical thinking skills that I do want you to develop. So the bottom has to be positive because it's being squared. So I'm really just checking the signs of the numerator. So if I plug in a negative number, less than 0, negative 2 times a negative number is a positive number. And if I plug in a positive number, negative 2 times a positive number is a negative number. That means my function has to increase before 0 and decrease after 0. Okay, so we're going to be increasing from negative infinity to 0 and decreasing from 0 to infinity. Okay, that means I have a local max at x equals 0. Okay, after I do this, I'm going to take my second derivative. Now, second derivative I want to do in a simplified form of my first derivative. Okay, if I look at this line, I need product rule. If I look at this line, I need quotient rule. Honestly, it doesn't matter. I'm going to go with the quotient rule. Okay. So my second derivative is going to be low x squared plus 1 quantity squared. Okay, d high, the derivative of negative 2x is negative 2. Minus high, negative 2x. D low, I'm going to drop down the exponent, reduce it by 1. The inside stays the same. Times the derivative of the inside is a 2x. All over x squared plus 1 squared, quantity squared. Low, right? Okay. So I warned you guys these are going to be algebra heavy problems. We've got to clean this up, which it's going to be hard to do. We're lacking space here. I wish I had a bigger board. Okay. If I clean this up, this first piece is negative 2 times x squared plus 1 quantity squared. The second piece is minus a negative, so plus, and I have a 2x times a 2 times another 2x. So that's going to be an 8x squared times x squared plus 1. And I'm going to be setting this equal to 0. Okay. I am going to, let's see, clean up some space over here. So let's remember that this was my horizontal asymptote, y equals 0. We'll come back to that. And I'm going to rework my second derivative here. Okay, so my second derivative is really, I'm going to factor out what's in common. So I can factor out a 2 times the quantity x squared plus 1. And if I factor that out of my first term, I'm left with negative the quantity x squared plus 1. And if I factor that out of here. If I factor it out of here, I'm left with let's see, minus 4x squared. No, plus 4x squared. Plus 4x squared. All over x squared plus 1 squared squared is x squared plus 1 to the 4th. Okay. I'm going to clean up that numerator one more time. And I'm going to have 2 times x squared plus 1 times, and these are very algebra heavy, and I apologize, but there's no way to get around it. I have a 3x squared minus a 1 here now. All over x squared plus 1 to the 4th. Okay. Let me clear some space. All right. Now, if I set this equal to 0, I'm going to look for the numerator to equal 0. Okay, so 2 can't equal 0, x squared plus 1 can't equal 0, 3x squared minus 1 can equal 0. So that's the only time that this is going to equal 0, when 3x squared minus 1 equals 0. And that would be when 3x squared equals 1, or when x squared equals a third, or x would equal plus or minus 1 over radical 3. It would be the square root of both sides, which would be 1 over radical 3. Okay. And I'm going to make a sign chart out of that. Where can I do this so that I'll have room to do the rest of this? Let's see if I can shove it down here. Sorry, guys. Okay, and 1 over radical 3 is like 1 divided by 1.7 something. So it's approximately like between 0.5 and 0.6. It's both positive and negative, okay? So I'm going to do a sign chart for f double prime and f, and my zeros are at negative 1 over radical 3 and positive, excuse me, I got hiccups, positive 1 over radical 3. Okay, so I'm going to have zeros on both of these. Okay, if I plug in something less than negative 1 over radical 3, now I'm plugging into my second derivative, which is really this crazy mother function. Okay, if you look here, look at this 2, has to be positive. Look at the stuff inside these parentheses, x squared plus 1, that has to be positive. Look at this piece, something to the 4th power, that has to be positive. So the only thing I'm looking at the signs on is the 3x squared minus 1. So if I plug in something less than negative 1 over radical 3, and here's where it's really helpful to understand that it doesn't matter what number I plug in. Let me do something like a negative 10. If I plug in something like a negative 10 for this interval, okay, that is so effective because I'm going to get negative 10 squared is 100 times 3 is 300 minus 1 is definitely a positive number. If I plug in something like 0, I'm just focused on this part because it's the only thing that can change signs, this part right here. If I plug in 0, it's definitely going to be a negative. If I plug in something bigger than 1 over radical 3, let's do positive 10, I'm going to definitely get a positive number. Okay, and then where f double prime is positive, f is concave up. And where f double prime is negative, f is concave down. So I'm going to be concave up from negative infinity to negative 1 over radical 3, and again from 1 over radical 3 to positive infinity. I'm concave down between those two weird x values from negative 1 over radical 3 to positive 1 over radical 3. And I have an inflection point. Pretend that's what that says. Let me try that again. At x equals plus or minus 1 over radical 3. Okay, so now I'm going to take all this information and graph this very, very, very weird rational function that has no vertical asymptotes but a horizontal asymptote. Okay, if you look at the actual function in question, I cannot have any negative y values for this function. The domain of it is all real numbers. Right? There's no x's I can't plug in because I can't have zeros in my denominator. My range is y is greater than 0 because I can't get negatives out of f of x. Okay, so I have a 0, not a 0. I have my y-intercept at x equals, my goodness, at the point 0, 1, right? That's my y-intercept. Okay, and I have points of inflection at negative 1 over radical 3 and at positive 1 over radical 3. Okay. All right. And again, because my range is greater than 0 and I know that I have horizontal asymptote at y equals 0, I'm going to have to approach the horizontal asymptote at both ends. Okay. If I look at this, I start out increasing and concave up. So I'm increasing and concave up until that point. Then I switch to increasing concave down. Okay, and then I switch to decreasing concave down, and then I switch to decreasing concave up again. Okay, and it's one of those weird rational functions that looked like a bell-shaped curve. Okay, but one of the ones that we didn't know how to really graph when we were in Algebra 2. And here we're using calculus, and yes, the algebra got messy, but I can produce a very effective, very accurate graph even without so easily distracted right now. I'm so sorry, guys. Even without doing all the crazy things that you were taught to do in your Algebra 2 and your pre-calc classes. Okay, so when you guys are doing your homework tonight, you're finding first derivative, making a sign chart with it, finding second derivative, making a sign chart with it, and then you're going to try to graph based on that. Good job, guys.